Well, greetings everyone, and we're going to finish up talking about two-dimensional kinematics today. And as usual, I've got a bunch of slides for you. There's an old movie called Speed, starring Keanu, who's from well, all sorts of movies now. But it was one of those movies that was pretty dumb, but very enjoyable. And you need movies like that every once in a while. So I enjoyed the movie Speed. Go watch it if you can. It's a fun movie. There's a bomb on a bus, and it will explode if the speed of the bus drops below 50 miles per hour. So the characters have to keep this bus going the whole movie at over 50 miles per hour, even as they're losing gasoline and all that. So it's a fun movie. But at one point in the movie, they have to jump over an overpass. There's construction on a highway overpass, and they have to jump the overpass because the overpass isn't complete in the middle. So there's a giant jump in the middle. And they do it. They're able to make the jump over the overpass, but it makes no sense from a physics perspective. The two sides of the overpass are like this, and they make the jump like right over the overpass, just directly like that, with no change in height. And you can't really go like that. It was a wide gap as well. If you're jumping like that, starting from one place and going to another place, then you need the place that you're starting from to be higher than the place that you're ending. Otherwise, you're just going to like crash into the side of the side. I don't remember if there was a ramp in that movie. There might have been, but it was not a big ramp. It as I recall, it was a pretty even thing. We would actually need something like that, and so it's easier to calculate when you've got a change like that. So let's actually do the math. The driver of the bus must make the jump over an incomplete highway overpass to survive. The gap which is jumped is 10 meters, which for everyone that grew up in the United States, it's probably a good idea to think, okay, 10 meters, oh yeah, that's about 33 feet. Just multiply by about 3.3, it's 3.28, and I'll give you these numbers if you ever need them on a test. But just remember, okay, I need to multiply that by about 3, and that way you can visualize it better. So the bus is traveling at 22.4 meters per second, which, if you remember what we talked about from the beginning of the semester, if you multiply the meters per second speed by a little bit more than 2, then you get the speed in miles per hour, which, well, this 22.4 meters per second is 50 miles per hour. So there's a reason for that right there. What is the difference in height from one side to the other? I give you all these equations right there to help you decide. First thing that we always do in a problem like this is draw it. And you can see my beautiful artwork here with a photorealistic bus that is driving off of this part of the highway, kind of arcing down. Remember, what is the shape that an object in free fall is going to make? It's going to be a parabola. It should always make a parabola or a section of a parabola as you jump off of something. And so that's a parabola. You can actually tell that it should be a parabola based off of the equations that you get, because you end up getting quadratic kinds of equations, polynomials, and it's a second order polynomial. So second order polynomial should give you a parabola when you graph it. And so it actually totally makes sense that you get a parabola there. I say, oh, I wrote 30 meters. That's not right. It's 10 meters. Or is it? Which number did I use? I actually did use 30 meters. Pardon me. The slides are wrong on that. I will update the slides with the more accurate information. But for now, I guess we're saying 30 meters instead of 10 meters. Initial velocity, 22.4 meters per second. And that means that we can start plugging in equations. And, well, we've got some heights, some speeds, some distances. Often when you do problems like this, you're going to end up using this equation with the final position is equal to the initial position plus the initial velocity in x, if you're looking at the x stuff, times the time that it takes for everything to happen, plus 1/2 times the acceleration in x times t squared. Oh, all sorts of stuff, but this is a very useful equation for this kind of thing. We can plug in initial velocity. Now, very often, we have to say initial velocity in x is equal to initial velocity times the cosine of theta, and initial velocity in y is initial velocity sine of theta. We don't have to do that here, because the bus goes directly horizontally off of this highway. I said that there's no ramp when I got that question in chat. There's no ramp here, and so if there's no ramp, there's no angle there. The angle is 0 degrees because you're going straight off the highway. So at 0 degrees, the cosine of 0 is 1, and the sine of 0 is 0. And therefore, initial velocity in x is just the initial velocity, and initial velocity in y is 0. I don't know why I was writing v, but it's 0. We can plug in the numbers that we know. I apparently used 30 when I was preparing this. So 30 meters is going to be the x final position. The x initial position, we can just say, oh, well, that's just the edge of the highway right there. And that's going to be 0. Because we're just going to measure things from there. If it's 30 meters across, then you can say that over here is 0 and over here is 30. That's fine. So 0 for that, 30 for that. V initial, 22.4 meters per second. That's because it's only going in the x direction, times the t that we don't know, plus 1/2 times the acceleration in x. Well, the acceleration in x is 0. In this case, and in any case involving projectile motion, because in projectile motion, you are only being pulled down by gravity. So being pulled down by gravity means that there's no force going in the x direction, and if there's no force in the x direction, there's no acceleration in the x direction, which we will get to next week, but that is the easiest way of explaining that for now. Remember, many of you already know that F equals ma, and in a particular direction, the force in the x direction, if this is 0, then the acceleration in the x direction also has to be 0. Anyway, this is just one equation and one unknown. We know everything except for the time, and therefore we can just solve for the time. That means that we know right off the bat how much time it takes to get from here, from this point at that edge of that highway to this edge, that line over here. It does not matter where h is. H could be all the way down there, h could be even much higher, but the bus will go from this somewhere along this vertical line to somewhere along this vertical line in 1.34 seconds. That's easy. This is one of those cases that solving for t is a lot more plain and obvious. So what do we do with the rest of it? Well, we can do the exact same equation with y. Y final is equal to y initial plus initial velocity in y times t plus 1/2 times acceleration in y times t squared. And you have several options for how to plug this in. You can either set this height to be 0, or you can set this height to be 0, and then have that be some negative height. It's just going to make a difference of which one of these is 0 and which one of these is unknown. One of them will be 0, one of them will be unknown. You can do it either way. I go back and forth on whether or not I want the initial point to be 0, 0, or like the lowest height to be a height of 0. Either one works, whichever one you're comfortable with. In this case, I said that the initial height, I'll just show you. In this case, I said that the initial height, the initial y is 0, and the final y, the final height, is negative h. If this is 0, if this line where it begins is 0, then it ends up h amount down from there. And so the final height, or the y final is going to be negative h because it fell by an amount h, which is the difference in height between one side of the jump and the other side of the jump. Okay, y initial I said was 0. Initial velocity in y I said was 0 because it's going just in the x direction at the beginning. So there is no y velocity at the beginning. Well, it's equal to 0. So it doesn't matter that it's multiplied by time. You just get 0 times something plus 1/2 times negative 9.8 because the acceleration in the y direction in free fall is negative 9.8 meters per second squared. It's negative g times t squared. This is, well, it would have been one equation and two unknowns. One equation, two unknowns, but we already solved for that t over there, just purely, I don't want to say by accident, but by happenstance, I suppose, we solved for t. We can plug that in there and just do our algebra. I multiplied both sides by -1 to get rid of the negative, and I got rid of the zeros there. And h is equal to that. That's just a bunch of numbers. The height, the difference in height between one side and the other side can be no more than 8.79 meters, or no less than 8.79 meters, excuse me. Let's just say that the bus exactly gets to its point right there, like in the movie, and so you can say 8.79 meters for the difference in height from one side to the other. I give you the answer there, although Stefan is probably right about rounding it. I show you my work, which I did just show you seconds ago, and so you can look over that again if you need to. And now another question, finding the maximum height. You throw a baseball at an angle of 45 degrees above the horizon at a speed of 20 meters per second. What is the maximum height of the baseball? How high up does the baseball get after being thrown at an angle of 45 degrees above the horizon at a speed of 20 meters per second? Again, never a bad idea to draw it out. I throw at 20 meters per second. The angle was 45 degrees. I'm going to reach some maximum height at some point. Remember, it should be a parabola or a section of a parabola. Eventually, it'll hit the ground again. Do we care about where it hits the ground? Not really. We really only care about the initial condition and the place where we're actually being asked a question. And so we're being asked, how high up does it go? So in this case, obviously not in all cases, but in this particular case, its range. Remember, range is how far along the ground it goes. The range doesn't even matter in this case. The delta x doesn't matter. This delta y matters at halfway through the problem. So we can ignore the second half of the motion. And one thing that we talked about very briefly is that when you get to the maximum height, when height is equal to its maximum, then the velocity in the y direction has to be 0. I want to make sure that that makes some sense. So I'm actually going to draw it out here. When you've got a parabolic trajectory like that you're throwing something, at this point, you are going in that direction, and that direction has components that look like this and look like that, x and y, the x component and the y component. When you're here, for example, then that is your velocity. And so you've got an x component and a y component. And when you are there at the maximum, then that right there is your velocity. And you have no y component, and it's all x component there. So you still got a velocity, but it's only in the x direction. And then when you're over here, you might have that as your direction of motion, and that is the x component, and that is the y component, for example. We're looking here, where it's at its maximum point, like that, the maximum height. So the velocity in the y direction should be 0. We can use that to our advantage, because we can use this equation. Vy final is equal to Vy initial plus acceleration times time. We're not being asked anything about how long it takes, but as usual, in a two-dimensional problem, we end up having to figure out something to do with time. And so why not use it here? We have the final height, or sorry, the final velocity. The final velocity of the baseball is going to be 0. The final velocity in the y direction is going to be 0. That's equal to the initial velocity in the y direction, which we can calculate, 20 sine 45, plus negative 9.8 times t. And that gets us some time that it takes to get to its maximum height. And then, if we go here, we can say, well, the initial height was 0. We're looking for the final height when it's at that point. We already figured out the initial y velocity there. We can plug in that time there and add 1/2 times negative 9.8 times that time again. And that should get us, there's the work, that should get us the right answer there. You might be able to see a potentially easier way of doing this problem. There are many ways of doing these kinds of problems, and I generally just show you one way of doing a problem. We can also do things like v final squared is equal to v initial squared plus 2a delta x, but let's make this for y. So vy final squared, which is 0 because you get to 0 speed at your highest point, is equal to vy initial squared, which is 20 sine 45, plus 2 times negative 9.8, because that's g, times my change in height, which I'm actually just going to call h. So this is 0 is equal to 20 sine 45 squared minus 2 times 9.8 times h. And this should get you the same answer. And so there's always going to be multiple ways of solving these kinds of problems. And sometimes I give you one way, sometimes I give you another way. They'll get you to the right answer at the end. Any questions on this one? So acceleration, when not given in the question, would always be negative 9.8. If the only thing acting on you is gravity, if the only thing acting on the object in question is gravity pulling you down, and if we're on Earth, of course, then the acceleration in the y direction will be negative 9.8 meters per second squared. In the x direction, it'll be 0. If we're on the moon, then it would be negative 1.6 meters per second squared in the y direction and 0 in the x direction. On Mars, it would be 3.8 meters per second squared in y in negative and 0 in x. That's for free fall problems. And free fall problems are by far the most common type of two-dimensional kinematics problems.